Swayam Prabha. Digital India. Educated India.
Welcome to lecture 35 on time series modeling and forecasting. In the last lecture, we discussed vector auto-regressive moving average processes and their invertibility and stationarity conditions. We derived the stationarity and invertibility conditions for these processes. We also obtained the Yule-Walker equations for vector auto-regressive processes. In this lecture, we will discuss the forecasting problem for vector auto-regressive processes. Another important topic which I am going to start from this lecture is causality. Causality of different economic time series is an important topic in the sense that it has drawn attention of many researchers in recent past. The person who had given this idea of causality, Clive Granger, got Nobel Prize of Economics for his work. So, I am going to discuss various aspects of Granger's causality in this lecture. So, first we consider the vector auto-regressive process of order 1 and then we will obtain the ACF of vector auto-regressive process of order 1. So, we consider the process is y t equal to phi y t minus 1 plus u t. Again we assume that expectation of u t transpose is equal to sigma u. Then by recursive substitution you can write this VAR1 process as a moving average process of infinite order. So, first we write y t equal to u t plus phi u t minus 1 so on plus phi to the power j u t minus j, and then the last term is phi to the power j plus 1 y t minus j plus 1 in this form. Then suppose lambda 1, lambda 2 so on lambda p are the eigenvalues of phi or phi transpose. Then as j turns to infinity, if phi to the power j turns to 0, then you can write the process as a MA process of infinite order. And you say that the process is stationary or stable, because when phi to the power j turns to 0, this last term vanishes as j turns to infinity, and you get a moving average representation of the process of infinite order. Then gamma 0 is equal to expectation of y t transpose. So, again expectation of y t transpose is equal to expectation of phi y t minus 1 plus u t into y t transpose. And then this is equal to phi, and here you have gamma y 1, and then expectation of u t y t transpose is equal to sigma u. Then gamma y 1 is equal to expectation of y t plus 1 transpose. So, gamma y 1 you can obtain as expectation of y t, and then you write y t plus 1 equal to phi y t plus u t plus 1, and then you have transpose of this. So, you get gamma y 0, actually you get expectation of y t transpose, which is gamma y 0, and then you have phi transpose, and expectation of y t u t plus 1 transpose is equal to 0. So, this implies that gamma y 0 is equal to phi sigma u phi transpose plus sigma u. Then gamma y 1 is equal to gamma y 0 phi transpose. You get from here. Gamma y L is equal to expectation of y t plus L transpose. Then you write y t plus L equal to phi y t plus L minus 1 plus u t plus L. Then you take transpose of this. So, the first term gives you expectation of y t plus L minus 1 transpose phi transpose, and expectation of y t plus L minus 1 transpose is equal to gamma y L minus 1 to phi transpose. And then by recursive substitution you obtain this is equal to gamma y L minus 2 phi transpose square and so on, gamma y 0 phi transpose to the power L for all L greater than or equal to 1. Now, suppose lambda is diagonal lambda 1, lambda 2, lambda p with the matrix of eigenvalues of phi transpose, and P be a lower triangular non-singular matrix such that phi transpose is equal to P lambda P inverse. Then you can write phi transpose to the power L is equal to P lambda to the power L P inverse, because phi transpose is equal to P lambda P inverse. So, then phi transpose say square is equal to P lambda P inverse P lambda P inverse. So, you get P lambda square P inverse. In general, you obtain phi transpose to the power L equal to P lambda to the power L P inverse. So, gamma y L is equal to gamma y 0 P lambda to the power L P inverse. From here, you substitute phi transpose to the power L equal to P lambda to the power L P inverse. Now, from this expression, what you observe if all these roots are, or all these eigenvalues are less than 1 in magnitude, then the elements of lambda to the power L exponentially decrease. Now, rho y L is actually equal to v to the power minus half gamma y L v to the power minus half, and then this is equal to v to the power minus half gamma y L is equal to p lambda to the power L p inverse, and then you have gamma y 0 here. And then you can write it as v to the power minus half gamma y 0 v to the power minus half v to the power half p lambda to the power L p inverse v to the power minus half. Now, this term is equal to rho y 0, and then you have this term. So, rho y L is equal to rho y 0 v to the power half p lambda to the power L p inverse v to the power minus half. So, for vector AR1 model, the correlations will exhibit a mixture of damped exponentials and damped harmonics depending upon whether the roots are real or complex, just like the univariate AR1 process. So, if a particular root is real, then you get damped exponential term, and if the root is complex, then naturally its complex conjugate is also the root, then you get a damped harmonic term. Now, we consider this example of VR1 model. Say you have y 1 t equal to 0.8 y 1 t minus 1 minus 0.4 y 2 t minus 1 plus u 1 t, and then you have y 2 t equal to minus 0.2 y 1 t minus 1 plus 0.6 y 2 t minus 1 plus u 2 t. So, you can write this process in vector form as y 1 t y 2 t equal to 0.8 minus 0.4 minus 0.2 0.6 y 1 t minus 1 y 2 t minus 1 plus u 1 t u 2 t. And suppose sigma u is equal to 1 1.45, and here in the off diagonal elements you have 0.7 and 0.7. Then to check whether the system is stable, you have to calculate the roots of determinant of I 2 minus phi z, or this is your phi. So, you get 1 minus 0.8 z, then here you get 0 minus minus 0.4 z. So, you get 0.4 z here, then you get 0.2 z here, and then 1 minus 0.6 z. So, if you take determinant of this matrix 2 by 2 matrix, then you obtain 1 minus 1.4 z plus 0.4 z square, and then you write it equal to 0. And then the roots of this equation are z 1 equal to 1 and z 2 equal to 2.5. You can easily verify it. Now, one of the roots is equal to 1. So, the model is not stable. just like the univariate time series, it has a unit root. Again we consider this VR1 process. So, here the phi matrix is 0.2, 0.6 and in the off diagonal elements you have minus 0.4 and minus 0.2. And then you have taken sigma u as 1, 1 and in the off diagonal you have 0.5, 0.5. Then the roots are obtained by the equation determinant of 1 minus 0.2 z, here you get, then minus 0.4 z, so you get plus 0.4 z here, then you have plus 0.2 z here and 1 minus 0.6 z here. And if you take determinant of this matrix, you obtain 1 minus 0.8 z plus 0.04 z square. Then you write it equal to 0 and you obtain the roots. So, solve it for z and the roots are 5 into 2 plus minus under root 3 and then you can easily verify that both the roots are larger than 1 in modulus. So, in this case the system is stable because both the roots are greater than 1 in magnitude. Now, we obtain the variance covariance matrix of I, gamma y 0 is equal to, you have phi gamma y 0 phi transpose plus sigma u and gamma y 1 is equal to gamma y 0 into phi transpose. So, basically the problem is to obtain gamma y 0 by solving this equation. So, we write this equation in scalar form. So, for obtaining gamma 1 1 0, gamma 2 2 0 and gamma 1 2 0 which is equal to gamma 2 1 0, we have to solve these equations, say 0.96 gamma 1 1 0 equal plus 0.16 gamma 1 2 0 minus 0.16 gamma 2 2 0 is equal to 1. So, what you have to do? You have to multiply this gamma 0 or gamma y 0 which has elements gamma 1 1 0, gamma 2 2 0 and in the off diagonal you have gamma 2 1 0 by phi before gamma y 0 and then you have to post multiply it by phi transpose and then you add sigma u and then you have say at 1/1th place you have gamma 1 1 0 here. So, you just compare the 1/1th element of right hand side with the 1/1th element of left hand side and you get this first equation. Similarly, you compare the 1/2th element of right hand side with the 1/2th element of left hand side which is gamma 1 2 0. You get the second equation and then if you compare the two 2th elements means gamma 2 2 0 equal to the 2/2th element of phi gamma y 0 phi transpose plus the 2/2th element of sigma u. Then you get the third equation and then we solve all these three equations for gamma 1 1 0, gamma 1 2 0 and gamma 2 2 0 and your solutions are gamma 1 1 0 equal to 1.485, gamma 1 2 0 is minus 1.057 and gamma 2 2 0 is 2.132. Then you can obtain the instantaneous correlation between y 1 and y 2 as say gamma 1 2 0 divided by under root gamma 1 1 0 into gamma 2 2 0 to the power half, and then gamma 1 2 0 is this minus 1.057, and then you have the value of gamma 1 1 0 also here, gamma 2 2 0 also here. So, finally, you obtain minus 0.594. Now, we consider vector autoregressive moving average process of order p q. So, the process is phi b y t is equal to delta plus theta b u t, or you can write it as y t equal to delta plus summation over j equal to 1 to p phi j y t minus j plus u t plus summation j equal to 1 to q theta j u t minus j. Here actually phi b is equal to I k minus phi 1 b minus so on minus phi p b to the power p, and theta b is equal to I k plus theta 1 b so on plus theta q b to the power q. Now, this vector autoregressive moving average process is stationary if roots of determinant of phi b equal to 0 lie outside the unit circle. So, just like the univariate processes, for checking the stationarity of the process, you have to focus on roots of the determinant of phi b equal to 0, and if all the roots lie outside the unit circle, then you say that the process is stationary. Then for invertibility, you have to consider the roots of determinant of theta b equal to 0, and if all the roots lie outside the unit circle, then you say that the process is invertible. Now, we consider the problem of forecasting using vector autoregressive process of order p. The forecasts for VR processes are obtained as say y hat t 1 step ahead forecast when you have information up to time t is equal to expectation t y t plus 1, where this expectation subscripted by t denotes the expectation given the information up to time t. And since the observations up to time t are given, so this is equal to delta plus phi 1 t plus phi 2 t minus 1 so on plus phi p t to power t plus phi p y t minus p plus 1. Then since you have information up to time t, all these y t minus 1 so on y t minus p plus 1 are known. Then for obtaining the two step ahead forecast y hat t 2, you have delta plus phi 1, then actually at this place you have y t plus 1, and you do not have the value of y t plus 1 because you have information up to time t. So, you take expectation t y t plus 1 here. So, you get y hat t 1 plus phi 2 y t plus 1 plus phi p y t minus p plus 2 and so on. So, this is how you can obtain the forecast for vector autoregressive processes. Then suppose we consider the moving average representation of this vector autoregressive process. Then the moving average representation is say y hat t 1 is equal to mu plus psi 1 u t plus psi 2 u t minus 1 plus so on. Actually, you have y t plus 1 equal to mu plus u t plus 1 plus psi 1 u t plus 1 Then if you take the difference between y t plus 1 and y hat t 1, then y t plus 1 minus y hat t 1 is equal to u t plus 1. So, this u t plus 1 gives you the forecast error. So, basically we use the auto regressive representation to generate forecasts and moving average representation for calculating the corresponding forecast errors. The difference between the actual value and forecasted value is the forecast error. Now, we consider Granger causality. Now, suppose we have more than one time series, then the question is whether data generating processes of these time series are independent of each other or dependent on each other. And if yes, if these data generating processes are dependent on each other, then what is the dynamic mechanism of dependence? Remember, in bivariate regression or in multiple regression analysis, we have pairs of observations. For example, suppose you take bivariate regression case, then you have pairs of observations x I y I on independent and dependent variables, and then we express y I as a function of x I. This regression model or linear regression between y and x does not consider the dependence between y I and x I minus 1 or y I and y I minus 1 or y I and x I minus 2. And the reason is quite simple, because in regression we assume that different observations are independent. So, the pair x I y I is not at all related with x I minus 1 y I minus 1. These two are independent observations. Now, this is not the case with time series analysis. Suppose you have two time series and at time t you have taken the observation on x and y as x t y t. This is also a pair of observation. Now, suppose you want to establish a relationship between y and x, then y t may depend upon x t. But this is not the end of the story. Y t may depend upon y t minus 1 also. Y t may depend upon y t minus 2. Then y t may depend upon x t minus 1. It may involve x t minus 2. So, that is why the usual regression techniques which we consider for static models do not work for time series models. For time series models, you have to develop this kind of dynamic relationships where y t can be expressed as the past values of y t's also, or the current value of x t or past values of x t's also. So, this is how the running the regression for time series data differs from running the regression for usual static models. Now, two major challenges are correlation does not imply causality. Sometimes your two series may be highly correlated, but one may not be causing the other series, and it is important but difficult task to distinguish between these two. So, you must distinguish between correlation and causality. Correlation does not always imply causality. Then the causal relationship among variables might disappear when the previously ignored common causes are considered. Means suppose it appears that the two variables have causal relationship. But suppose you have ignored some of the common causes, then if you consider those common causes also in the relationship, then that causal relationship among the variables may disappear. Then we take two assumptions. The future cannot cause the past. Yt minus 1 can cause Yt, xt minus 1 can cause xt. Xt can cause Yt, or xt minus 1 can cause Yt. But Yt cannot cause Yt minus 1, or xt cannot cause Yt minus 1. So, the future cannot cause the past. The past causes the present or future. Then a cause contains unique information about an effect not available elsewhere. This also we assume that a particular cause contains a unique information about an effect which is not available elsewhere, means with other lag or with other variable. Now, a variable x is causal to variable y if x could be interpreted as a cause to y or y as effect of x. So, if x can be interpreted as a cause to y or y is an effect of x, then you say that the variable x causes variable y. To be more clear, suppose It is the total information set available at time t, and this information set contains the two time series x and y. Means you can say this is It contains all the observations on x and y up to time t. So, this is the information set up to time t. Then by xt curl we denote xt, xt minus 1, so on. So, this is the set of all current and past values of x up to time t, and yt curl denotes the set of all current and past values of y up to time t. Then sigma square dot denotes the variance of the corresponding forecast error. Now, we define Granger causality, which was first given by Clive Granger in 1969. Xt is said not to Granger cause y if for any h greater than 0, f yt plus h given it is equal to f yt plus h given it minus xt curl, where f denotes the conditional distribution and it minus xt curl is all the information except xt curl. So, this is the conditional distribution of yt plus h given it, the information set up to time t, and this it contains both x t curl as well as y t curl, or this is the distribution of h step ahead value of y given the information up to time t, and this right hand side gives you the distribution of y t plus h given the information up to time t minus the information available with x, which is x t curl. So, you are excluding the information contained in x, and then both the conditional distributions are same. This implies that this x t curl has no information about y t plus h. So, if you are using x t curl for predicting the value of future value of y, then it will not help you. It does not have any information about y t plus h. That is why if you remove this information from the total information set, you take I t minus x t curl, then the probability the conditional distribution is not affected. So, we say that x t is set to not to Granger cause y t. Now, in practice the whole distribution f is generally difficult to handle empirically, and we turn to conditional expectation and conditional variance. Then we define simple Granger causality. The definition is x is simply Granger causal to y if and only if the application to an optimal linear prediction function leads of sigma square y t plus 1 given I t less than sigma square y t plus 1 given I t minus x t curl. So, you are using any linear prediction function for predicting one step ahead value of y, and on left hand side here you have the variance of the linear prediction function when while predicting the value of y you are using all the information contained in I t, sigma square y t plus 1 given I t. On the right hand side you have excluded the information contained in x, means x t curl. So, you are taking the information set I t minus x t curl. The total information available up to time t excluding the information about x's, that is x t curl, and then again you are using a linear predictor for y, and this is the variance, and variance of left hand side is less than the variance of right hand side, means if for predicting the value of y you are making use of information about x, then the variance reduces, or if along with the other information you also utilize the information contained in x up to time t, means x t curl, then it is going to improve your predictor. It has lower variance. So, you reach to the conclusion that if this condition is satisfied, then the current and past values of x are used, future values of y can be predicted better. They have lower variance. And then you say that x is causal to y, or x is Granger causal to y. Now, we define instantaneous Granger causality. X is instantaneously Granger causal to y if and only if the application of an optimal linear prediction function leads to sigma square y t plus 1 given I t x t plus 1 is less than sigma square y t plus 1 given I t. Now, remember I t is the information available up to time t on both y and x, and this is the variance of linear predictor using the information available up to time t. Then on the left hand side you have also added the information on x at time t plus 1. Then the variance of the optimal linear predictor decreases. It means, if you include x t plus 1 also, it is going to improve your predicted value, in the sense that the predicted value has lower variance. It means x t plus 1 also has some information about y t plus 1. So, this kind of causality is known as instantaneous causality or instantaneous Granger causality. So, if this condition is satisfied, this means the future value of y, say y t plus 1, can be predicted with a smaller forecast error variance if the future value of x, x t plus 1 are used in addition to the current and past values of x. So, as soon as x t plus 1 appears, it affects y t plus 1 instantly. So, that is why this causality is called instantaneous causality. Then feedback. There is feedback between x and y if x is causal to y and y is causal to x. So, x is causing y and y is causing x, then we say that there is a feedback between x and y. So, there are 8 different exclusive possibilities of causal relationships between two time series. Say x and y are independent, we use this notation. If x and y are independent, or sometimes we write like this within bracket x y. Independent means neither x is causing y nor y is causing x. Then there is only instantaneous causality. This is the notation for instantaneous causality. So, only x t plus 1 is affecting y t plus 1, and the past values of x t are not affecting or not causing y t plus 1. So, only the current value is causing y t. Then x is causal to y without instantaneous causality. Means for predicting y t plus 1, if along with I t you also include x t plus 1, then this is not going to improve your predicted value. Then y is causal to x without instantaneous causality, just like the previous case. Then x is causal to y with instantaneous causality, means both the past values of x are causing y and then the current value of x is also causing y. Then y is causal to x with instantaneous causality. Then there is a feedback without instantaneous causality, means x is causing y, y is causing x, but in both the directions there is no instantaneous causality, and there is feedback with instantaneous causality. So, x is causing y, y is causing x, and both have instantaneous causality also. Now, you consider this bivariate AR1 process, y t x t equal to phi 1 1, phi 1 2, phi 2 1, phi 2 2, y t minus 1, x t minus 1 plus u t v t. Now, the four possible causal directions between x and y are, say, feedback, x is causing y, y is causing x. So, H naught is this, phi 1 1, phi 1 2, phi 2 1, phi 2 2, all are non-zero. So, if you consider the first relationship, y t equal to phi 1 1 y t minus 1 plus phi 1 2 x t minus 1. So, both here x is causing y, then from the second relationship you observe that y is causing x. Independence, if phi 1 2 is 0 and phi 2 1 is 0, then y t is equal to phi 1 1 y t minus 1, x t minus 1 is not involved here, and x t is equal to phi 2 2 x t minus 1. So, neither x is causing y nor y is causing x. Now, suppose phi 2 1 is equal to 0, then what happens? X is causing y, but y is not causing x. In the first relationship, y t is equal to phi 1 1 y t minus 1 plus phi 1 2 x t minus 1. So, x is causing y. In the second relationship, x t is equal to phi 2 2 x t minus 1. So, y is not causing x. On the other hand, if you take phi 1 2 equal to 0 and phi 2 1 is not 0, then y is causing x, but x is not causing y. So, these are the four possible causal directions for AR1 process. Then you have two stage testing procedure. You test H1 against H naught. H1 is independence, H naught there is a feedback. Then H2 against H naught, one direction causal relationship, and H3 against H naught. And if necessary, test H1 against H2 and H1 against H3, independence against one direction causality. So, these are the two stage testing procedures. Now, an equivalent definition can be obtained using MA representation. So, this is the MA representation for y t, MA representation of infinite order. Here, suppose we use L y t equal to y t minus 1. So, L is the lag operator. This is actually same as the backward shift operator B, which we were using earlier. So, I have slightly changed the notation, and now I am using L for this lag operator. So, psi j k I is the jkth element of psi I. Then a necessary and sufficient condition for variable k, not Granger cause variable j, is that psi j k I is equal to 0 for all I equal to 1 to so on. So, the jkth element of this psi I is equal to 0 for all I. Then the variable k, not Granger cause variable j. So, this is the necessary and sufficient condition if you consider the moving average representation. Then if the process is invertible, then you can write it as an autoregressive process of infinite order. Then pi j k I is the j kth element of pi I. Now, if there are only two variables or two group of variables j and k, then a necessary and sufficient condition for the variable k not to Granger cause variable j is that pi j k I is equal to 0 for all I. Now, for a VR1 process with dimension equal to or greater than 3, pi j k I equal to 0 for all I is sufficient for non-causality at h equal to 1, but it is not a sufficient condition for non-causality at h greater than 1. So, up to order 2 means for two variables or for two group of variables, this kind of condition is necessary and sufficient pi j k I equal to 0 for all I. But if you have more than 2 time series, means 3 or greater than 3 time series, then this condition is sufficient for non-causality at h equal to 1, but it is not sufficient for non-causality for h greater than 1. Now, variable k might affect variable j in 2 or more period in the future via the effect through other variables. For example, if you take this 3-dimensional VA vector autoregressive process of order 1, VAR1 process, then y 1 is equal to phi y naught, y 2 is equal to phi square y naught, then phi matrix is equal to this. You can take a square of this, you get phi square. Now, notice that this element of phi is equal to 0, whereas corresponding element of phi square is not equal to 0. So, if you consider this third equation, then y 3 t, or you take t equal to 3, then y 3 3 is not influenced by y 1, but it is influenced by y 1 1 because of this element. So, causality is defined for all x h greater than 0, not just for h equal to 1. And causality for a particular h is neither necessary nor sufficient for some other legs. In the previous example, there was no causality for leg 1, but there was causality for leg 2. Then it is important to understand the causal mechanism by which yt's are produced. And then the two main tasks in causal inference are defining the set of hypotheses based on some economic theory, and then identifying causal models from data, which require estimation and hypothesis testing theory. Now, in this lecture, we have considered the causality for multivariate time series models, and we have also defined Granger's causality. Then there might be several forms of Granger causality. It may be a feedback, it may be instantaneous causality, it may be one directional, it may be two directional. So, all these issues we have discussed in this lecture. In the next lecture, we will consider different causality tests, and we will consider this causality issue in more detail. So, this is so here I am going to stop. Thank you.
Hello and welcome to this piece of literary snippet. Perhaps the most popular literary genre after novel is the short story. Sharp, compact narratives whose charm lies not only in what is said but also in what remains unsaid. Today I'll be reading one of the shortest instances of a short story that I have ever encountered. And indeed, the very charm of this particular story that I'm going to read out today lies in the way it abruptly ends. It is an ancient tale from Mesopotamia which has been retold by several authors, among whom the name of Somerset Maugham stands out. The adaptation that I'll be reading out is perhaps the closest to the one that Maugham wrote. The story is titled, in all of its adaptations almost, as Appointment in Samara. Here is the story. A merchant in Baghdad once sent one of his servants to the market. The servant was supposed to buy provisions for the merchant, but when he returned, he came back empty-handed. Indeed, the servant had all gone white, and trembling with fear, he told his master that he had met death in the marketplace. When I entered the market, the servant said to his master, I was jostled by a woman, and when I turned to look at her, I saw that she was death. I am very scared, master, because death looked at me with a threatening gesture. Can you please lend me your horse so that I can fly away from Baghdad to the town of Samara and thereby escape death? The master, being a good man, gave his servant his best horse and saw him gallop off to Samara to escape death. Then the master himself went to the marketplace and confronted death. Why did you make a threatening gesture to my servant? Asked the master to death. And death replied, it was not a threatening gesture. Rather, it was a start of surprise. I was astonished to see your servant here today, because this evening I have an appointment with him in Samara. See you in the next episode of Literary Snippet.